Hi everyone, it's Mr. Molekash, back again for another fun-filled week of calculus. I hope you've been enjoying these videos. I know some of them are crazy long, and I hear you. I would like to suggest that if a video is long, that you don't watch the whole thing at once. You split it up into pieces. Remember, I'm lecturing for an entire week's worth of material all in one video, so put yourself into bite-sized chunks. If you need to watch a little bit every day and take notes, you can do that. Now, having said that, this week our videos should not be that long. We'll see how it goes, but the two if you look in the pacing guide for my students in my course, this week there's a lot of stuff, right? There's extreme values, something called the MVT, which I'll tell you in a minute is really the mean value theorem, and then Rolle's theorem, which is a special case of the mean value theorem. And then that's all in section 3.2 in the NC State text. This is Mr. Molekash's text over here, but the book that I wrote. But the first derivative test, concavity, and second derivative test, we'll do more of that next week. I do want to talk about that a little bit, though, just to give you a little bit of a preview of what all this stuff is and why we're learning it. Okay, so just kind of a really brief overview of what we're going to talk about. And it really has to do with, given a function, excuse me, my head's itching, given a function on a closed interval, okay? So if we have a function on a closed interval, maybe like this one, right? From, say, -1 to 2 or something like that. We want to find its extreme values. So for that, we use this thing called an extreme value theorem. And it's a pretty important result in calculus. And yeah, here we go, extreme value theorem. So put that up there for your viewing pleasure. But again, I just kind of want to give you an overview of what we're talking about. So let's say that we have this entire function, maybe a cubic function or something like that. Okay. We know if we look at the entire domain of the function that there is no minimum and there's no maximum, because the range of this function runs from -infinity to infinity, right? So there's no extreme value as far as the absolute smallest y value or the absolute largest y value. However, if I draw a box around a portion of this function and we have a closed interval, say from x equals a to x equals b, okay, now there must be a largest y value and a smallest y value in that box somewhere, right? So on a closed interval from a to b, as long as this function is continuous, so there's no breaks in the graph, there's no removable discontinuity, asymptotes, anything like that, as long as we have continuity, and not even differentiability, right? So even if there's a sharp point or something like that, there has to be a biggest y value and a smallest y value in the closed interval. Okay, now without that black box being drawn there, we wouldn't be able to say that, right? I don't know what just happened. That is bizarre. Let's see if I can try that again. Oh, wow. Everything appeared kind of 3 times there. That is very weird. At least it looks like it's three times on my screen, so we'll try that again. But in the case of that cubic function. Okay, later on next week you won't be able to find an extreme minimum or an extreme maximum, but what you will do is you might find a minimum or a maximum that's called a relative max, right? So let's say that this is, you know, C f of C. Okay, this is the biggest y value in the neighborhood around that point. So remember the whole epsilon delta thing we talked about with limits, and I alluded to that and showed you where that was in your textbook. That's kind of what we're doing, right? We're looking very, very close to this point, in the neighborhood of this point, if you will. That is the largest y value. In the small delta epsilon neighborhood, very tiny box around that point, that would be the maximum. Okay, and similarly, there's another, you know, maybe we could say there's a C2 comma f of C2, you know, that ordered pair, you know, relative to the points nearby. That is called a relative minimum. So in next week's stuff, when we're doing the first derivative test and we're looking at the second derivative test and all this kind of stuff, the first derivative test is going to be used to find these points that are maximums or minimums relative to the points nearby, and those are called relative minimums or relative maximums or relative extrema. Okay, today's video is going to cover absolute extrema on a closed interval. So we're going to draw a box around a portion of the graph, and we're going to use calculus to find out where the maximum or minimum is in that box. Okay, now another thing that you will need to know about just for next week, and I don't, yeah, I guess Epic Pen is having some epic problems on my Mac. Sorry about that. But getting back to that function, okay, there is some vocabulary you'll need to know for next week, and that is this word concavity. So we say a function is concave down if it's cupped down like this. So say from here to here, this part of the graph is concave down, and then the part right after that is starting to curve upwards like that, so that would be concave up. Okay, and it turns out that the second derivative of a function tells us about the concavity. Okay, but that's really all I want to talk about for right now, because the mathematics behind all this stuff is very, very involved, much too much for us to include in today's video. Okay, but I just do want to give you guys a heads up and a little preview of what's to come next week. For my students, next week's video will come out right before your fall break. So you'll have a chance to either watch this over fall break or that kind of thing. Okay. All right, so let's talk about what the extreme value theorem says. It's over here in my book. The extreme value theorem says if a function is continuous on a closed interval, oh, that's really important. Continuity is a necessary condition for this theorem. So if you've got a hole in your graph, if you've got an asymptote, this function doesn't apply, this theorem doesn't apply. All right. If that is the case, and we have a closed interval, it will attain at least one absolute maximum value and at least one absolute minimum value on that interval. So that is a theorem. Super important that you get that. Okay. Now we also need to make the following definition, and we're going to need to explore this theorem with things called critical numbers. Okay. So critical numbers for a function f is where value, the derivative is equal to 0, or when the derivative is undefined. A critical number for f must be in the domain of f. Okay, so what does that mean? Let me show you some critical numbers of functions. right, so here's three functions that I'm drawing the pictures of, and I'm going to highlight for you in pink, I guess. I like the pink. Okay, so this, if this is x equals c, this is a critical number. Why is it a critical number? Because the derivative there is undefined. Remember, sharp points make derivatives that are undefined. We talked about that in a previous video. If the derivative is 0, then the tangent line is horizontal, right? So this is another critical point. We can say C2. Let's just start calling these different critical points. Here's another one. Okay, and if a function is not continuous, then it's automatically not differentiable, right? The derivative doesn't exist at this point because it's discontinuous, right? So differentiability implies continuity, but if you're not continuous, then you can't be differentiable, right? So over here, like let's say at this point we have a x equals c4, and the y value of c4 would be where this closed dot is, okay? So for this one, the extreme value theorem does not apply to this function. Even though there's a critical point, or critical number, sorry, there's a critical number there. The critical number is the x coordinate of the critical point, I suppose. But why doesn't this apply? Because remember, we have to have, function has to be continuous for this theorem to work out, right? So we're using, you know, this vocabulary word talking about critical numbers where either the derivative doesn't exist or the derivative is 0. But here, the extreme value theorem is not going to apply to this function, okay? So really important that we get that. Okay. Now, both of these lead to the following fact. A continuous function on a closed interval a to b will have its absolute extrema at either a critical number at x equals a or at x equals b. So let me go back to the picture that I drew earlier, the cubic function, right? And remember, I drew a box somewhere, right? So here's a box. Okay. And we're going to say that, let's see, right here is x equals a, and right here is x equals b. Okay. So the smallest y value occurs at x equals a, right? So at x equals a, f of a is the absolute min. You can see that on the graph. It's the lowest y value in the box. Not on the entire graph, just on the closed interval, right? On the closed interval. All right. So, but the extreme value might not happen at the endpoint. It might be that that at a critical number right here, that this is actually higher than this, right? So we could have a critical number where critical number is the y value of that critical point is the absolute maximum on the closed interval. So the candidates for absolute extrema, for the extreme values, are either at the endpoints or at the critical numbers. And that is what we're talking about here. Okay. Okay, so let's take a look at an example that I've typed out here. See if I can get my mouse moving up. Okay, so the above statement is called the candidates test for absolute extrema because it lists the x values where the extrema occur. To see how this plays out, let us consider the following examples. And I'm just going to do the first one for the purpose of this video. If you want a copy of my textbook, this single variable calculus for the AP student, just leave me a comment and I will reply with a link to this book. It's freely available to anybody who asks for it. All right. So if you want more examples, you can get as many as you want that I've written in the book. All right. So here's our function, right? Find the absolute extreme values of the function f of x. Sorry about my handwriting. Typing is much better than handwriting, isn't it? So here's our function. It's a cubic function. And we have the closed interval, which I'll write in interval notation from -1 to 1. Okay, so the function is only defined on that closed interval. In other words, we don't care what happens before -1, and we don't care what happens after 1. Okay? So we are going to list candidates. Okay, and we're going to list the x values of those candidates are either -1 or 1. By the way, you don't have to list them in order like I did. Or any critical numbers. So to find out if there's critical numbers, we have to look at where the derivative is 0 or undefined. So to find out what this number is, this is the discussion over here, I'm going to take the derivative of this function. And this is a pretty easy one using the power rule. By the way, my students, in recent days, I've been grading labs, and you guys have been working way too hard on your derivatives. You know, work smarter, not harder. If you can divide by x, or you can simplify things algebraically, it's a whole lot easier on you later on. All right, so anyway, here's our derivative, right? And remember, we want the derivative to be 0 or to be undefined. Well, this is a parabola. It's defined everywhere for all values of x. Of course, if it's defined everywhere, it's defined on the closed interval. So we don't have any critical numbers where the derivative is undefined. So what we're going to do is we're going to set the derivative. So critical numbers are solutions to where this derivative is equal to 0 on the closed interval given to us. Okay, so we're going to solve this by factoring and setting each factor equal to 0. We get x equals 0 or x equals 1. Well, 1 was already an endpoint. We listed that as a candidate. So the only other candidate for a critical number is 0. And incidentally, yes, an endpoint can also be a critical number, which means that right at the endpoint you're going to have a horizontal tangent. And we'll show you the graph here in a moment. Okay, so now I just plug these back into my function, not into the derivative, into the function, right? So putting 0 in there is pretty easy. I get y equals 1. If I put 1 in there, I get 0, because that's 2 minus 3 plus 1. And if I do -1, I get -2 minus 3 plus 1, right? Okay, so it's just as simple as to find the extreme values. The smallest one is the minimum, and the biggest one is the maximum. So how do we say this, right? How do we say the answer to this? Okay, so the absolute maximum value is 1, and it occurs at x equals 0. So the highest y value on the graph in this closed interval is 1, and it happens at x equals 0. See right there on the graph. Okay. The absolute minimum is -4, and that happens at the left endpoint right here. And the right endpoint also, if you kept on going after this, you'd see there's a horizontal tangent there, but 0 is not the largest or the smallest y value on the interval, but it was a candidate for 1, so we had to look and make sure, right? So again, the biggest one of these is the maximum, and the smallest one of these is the minimum. So that's how that works out. Okay. There's another example here. I'm not going to go through that, but again, if you want it, you can just type a comment below, and let me know and I'll give you a copy of this book. I'll put the link down there for you. Okay? All right. So the next thing that we need to talk about is a special case of this theorem. Well, it's not a special case of this theorem. It's a different thing. I'm getting ahead of myself. Let's scroll down to page 72 here. The next part of this video is to talk about this thing called the mean value theorem. The mean value theorem. And the mean value theorem is written in, I guess, symbolic notation. Yeah. So this theorem involves the slope of a secant line, if you remember that from earlier, right? A secant line is a line drawn through two different points on a graph of a function. And a slope of a tangent line drawn at a point between the other two. And you'll see what I mean in a moment. But this is called the mean value theorem, and the theorem is written as follows. If f is a continuous function on a closed interval from a to b, there's a closed interval again, so continuous, very important. You need to know that your function has continuity on the entire interval, including the endpoints, closed interval, and differentiable on the open interval. So that means we don't want any sharp points in the middle of the function's closed interval, right? And anything like that. Then there must at least be one value c in the open interval a to b such that f prime of c equals f of b minus f of a over b minus a. All right, now let me talk about this formula a little bit. This is the slope of the secant line is on the right side. So that's basically y2 minus y1 over x2 minus x1, right? Rise over run. That's what's going on. So the secant line is down here in this picture. And to find the slope of that line, I do y2 minus y1, right, divided by x2 minus x1. So there's the slope of the secant line. I'm going to call this the secant line. Okay. So the theorem is saying, hey, if you've got a function that's continuous everywhere on that interval, including the endpoints, and it's smooth, it doesn't have any sharp points or jagged edges or anything like that, so it's differentiable on the interval, then there has to be a place somewhere in the middle of this where the slope of this tangent line has the same exact slope. So in essence, the secant line and the tangent line are parallel for at least one value of c between a and b. Okay? And the slope, of course, is the derivative evaluated at c. Okay? And in recent questions, in recent videos, I told you how to find the equation of the tangent line. Right now, we're just looking at the slope of the tangent line evaluated somewhere in the interval, okay, between a and b, strictly between a and b, not equal to a, not equal to b. Okay, so again, the essence of this theorem is saying that as long as I've got a continuous and differentiable function, somewhere in the middle of this, I'm going to have a tangent line that is parallel to the secant line drawn between the endpoints. Okay. All right. Now, what you're going to have to do, if you're one of my students, and if you're an AP student, you're going to have to do the same thing. If you're taking AP Calculus, you may have to find the value of c that's guaranteed by this theorem. Okay. So, but let me show you a picture of a theorem, not a theorem, a picture of a function where the theorem does not apply. We talked about that earlier in the video, right? Theorem does not apply. Why does the theorem not apply to this function? The theorem, the condition that f be continuous is important so that f of c is defined. We have to have of c and f of c everywhere in the interval to look for that point, right? The condition that f be differentiable is important because the function may not have any value of c where the tangent line and secant line have the same slope as illustrated in the figure below. See, here's a secant line, but if I draw all the tangent lines, these are going to be too steep, and these are going to be negative slopes instead of positive slopes. So there's no tangent line that's parallel to a secant line. And the reason why is because the function was not differentiable on the interval, right? So the condition that the function be nice and smooth, differentiable, is a necessary condition. Okay. All right, so let's take a look at the bottom. Here there's a statement here, and then after we do this, I'll scroll back up a little bit and tell you about the special case of the mean value theorem called Rolle's theorem. I'll show you a picture of that in a moment. All right, so determine if the mean value theorem applies to this crazy function on the interval from 0 to 8. And let me write that out. Our function, it kind of took up 2 lines down here. So what is it? It's 3 times x to the 2/3 minus x on the closed interval from 0 to 8. So we want to know, does the MVT apply to this? Okay. Well, to figure that out, we got to see whether a function is continuous. And I apparently can't spell the word continuous. So let me fix that. Continuous. There we go. We need it to be continuous on the closed interval. And we need it to be differentiable on the open interval. Okay. So let's take a look at what the function is. It doesn't have any asymptotes. There's no denominator. There's no issues. Now we're doing cube roots, right? The cube root of x is defined for all real numbers, right? So certainly the numbers between 0 and 8 will work for all values between 0 and 8. So we've satisfied the continuity. Now for the derivative, we have to kind of take a look and see what the derivative of this function is. So let's take a look at that. We have to bring our 2/3 down. So it says 3 times 2/3 x to the negative 1/3. Negative exponent. I smell denominator. That may be a problem. Minus, okay, the derivative of x is 1. And these 3's cancel out. So let's clean this up. This is 2x to the negative 1/3 minus 1, otherwise known as 2 over the cube root of x, minus 1. Remember, the negative exponent means shift it to the denominator, and the 1/3 exponent means x to the 1 and do the cube root. Okay. Now, this is undefined at 0, right? This has a problem at x equals 0. If I put 0 into my derivative, it blows up. Something doesn't mesh right there. Okay. But remember, it only has to be differentiable on the open interval from 0 to 8. So I'm not including x equals 0 on this open interval. So once I get past 0, my derivative is good. So the answer to this is yes. The mean value theorem applies. Okay. X equals 0 doesn't make the function discontinuous, and I don't even get to use it for the differentiability condition, right? I'm only looking at the open interval from 0 to 8. Okay, now that we have said yes, what we're going to do is find the value of c guaranteed by the theorem. Okay, so let me spend some time erasing here. And, you know, Epic Pen on the Mac is not as good as it is on the PC, so I'm a little bit handicapped by the fact that I'm using a Mac right now. It's good that I can use, you know, my video recording software and all that kind of stuff. And the pen actually works pretty good with this software if you're a Mac user, if you have a writing tablet or something like I do. No Mac has a touch screen, so I can't write on the screen. I'm actually writing on a tablet. I bought a little writing tablet so that I could do these videos. But yeah, this isn't terrible. It's not terrible. It's not too bad. I can't get rid of all this stuff, but all right. So now we're going to do the find the value of C part. Okay, guaranteed by the theorem. So remember what the theorem says. There must be at least one value of C. So there exists C such that C is between A and B, and f prime of C is equal to f of B minus f of A over B minus A. And our A and B are given in the problem, right? There's A and there's B. Okay. And we also remember what our derivative was, right? So let's go put that, I erased that earlier, but that was what? 2 over the cube root of x minus 1. Okay, so f prime of C is 2 over the cube root of C minus 1. So there's our expression for the slope of the tangent line, right? Now for the secant line slope, I have to find f of B minus f of A, right? So let's see, I need to find f of 8 minus f of 0 over 8 minus 0. This is our secant line slope, right? So f of 8, let's see, the cube root of 8 is 2, 2 squared is 4, 4 times 3 is 12, 12 minus 8 is 4. I think I did that right. If I put 0 into my function, I get 0. Okay, so it turns out that this is 1/2. Okay, so the slope of the secant line for this crazy function, whatever it looks like, is 1/2. All right, so the way that we're going to work this out is we're going to set the expression for the tangent line equal to the value of the slope of the secant line, and we're going to solve that for C. And so I'll add 1 to both sides. So adding 1 to 1/2, that's 1/2 plus 2/2, which is 3/2. And then it looks like I can cross multiply. So I have 3 times the cube root of C equals 4. So the cube root of C is 4/3. And then I have to multiply that out 3 times. So C is 64 over 27. And sure enough, 64 over 27 is a number between 0 and 8. So this is the value of C guaranteed by the theorem. Okay? And yeah, I went through that pretty quick. So go rewind and slow the video down to half speed or whatever you need to do to find that out. Okay? All right, last thing I want to tell you about is Rolle's theorem, but before I do, I just want to show you like what was going on with this function, right? So let me zoom in here. This is the function that we were just dealing with on the closed interval from 0 to 8, and this 2.37 is the C value. So you can see, that the tangent line at that value does have the same slope as the secant line drawn between the endpoints. Okay? All right. Now, you're going to need to know what the heck Rolle's theorem is. It's important to know this because Rolle's theorem is a special case of the mean value theorem. Okay. So what am I talking about? The only difference with the mean value theorem, the statement that comes from the mean value theorem, the conclusion of the mean value theorem, right, was that f prime of C is equal to f of B minus f of A over B minus A, right? So this is the mean value theorem. Says if enough conditions are met, then this happens, right? Okay, and it's supposed to be the word if. If. blah, 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 right? If it's continuous in the closed interval, differentiable on an open interval. Okay. Rolle's theorem says, given those same conditions, if blah, 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 and the y value on the left is equal to the y value on the right, then f prime of c is equal to 0. And that's just a special case, right? Because if f of a and f of b are the same number, then you're subtracting the same thing minus itself, right? So you get 0 over b minus a. So in Rolle's theorem's case, what the function might look like is you might have something like this, right? You have, this is your x equals a, and then right across the way here is an x equals b, right? So your secant line is horizontal, right? And there's a value of c, and there's a value of c. There could be more than one c value guaranteed by the theorem. The theorem says there is at least one value c. There can be more than one. In fact, in the sine graph, there may be a whole bunch of them, depending on how big your interval is. Okay, so that's all that Rolle's theorem is. It just has that extra condition that the y values at the endpoints are equal, and then you set f prime of c equal to 0. All right, so that's what we're going to stop with this week. I hope you give me some feedback on these videos. I hope they're working out for you, especially if you're not one of my students. I would enjoy having a comment. And you know, if you want a copy of this book, let me know. I'll put it in the comment section, or even maybe in the description if somebody asks for it. But anyway, what we've done is we've looked at the extreme value theorem, the extreme values on a closed interval, the mean value theorem, and Rolle's theorem.